So we've just learned that molecules can be chiral if there's no plane of symmetry. We've also learned that tetrahedral carbons, if they have four different substituents attached to them, are called stereogenic centers or stereogenic carbons, and that this may lead to different types of stereoisomers, right? If there's one stereogenic carbon, then that leads to having two stereoisomers. They are enantiomers of one another. If there are two or more, then you have a possibility of diastereomers as well. So let's take a look at what happens when you have a ring in your molecule. And I'm going to tell you right now, it certainly complicates things quite a bit. And as a matter of fact, in the next chapter, we're going to really flush out what happens when you have the various types of rings. So for now, I just want to give you an idea about what you need to look for in terms of stereochemistry. And we're going to take a look at dichlorocyclopropane as an example. So cyclopropane, three-membered ring, it's planar. And if I put two chlorines on it, there's one of two ways that I can do so in terms of making a constitutional isomer. So I can have two chlorines on the same carbon or chlorines on carbon 1 and 2, basically. So the first example we're going to take a look at is 1,1-dichlorocyclopropane. Now, if you notice, I've drawn the line that's horizontal as kind of a bar. So that's coming out at me. I'm representing that as coming out at me. And then the point at the top is actually going behind me. Basically what that does is now I can think of the chlorines almost in line with one another in the plane. So in this scenario, with 1,1-dichloropropane, again, we have to think about stereochemistry. And do we have a stereogenic carbon? The answer is no. In this particular case, we don't. And as a matter of fact, you should be able to see that there is a plane of symmetry in this molecule. And because of that plane of symmetry, because there's no stereogenic carbons, there are no stereoisomers of 1,1-dichloropropane. So 1,1-dichloropropane only exists in one form. Now let's take a look at 1,2-dichloropropane. And if you look closely, now we have two stereogenic centers, right? We have that each one of these carbons is a stereogenic carbon. And if I think about spatial relationships of the two chlorines with one another, I can, in a ring, we've seen that substituents can be on opposite sides of the plane of the ring, or they can be on the same side of the plane of the ring. Now, when the chlorines are on the same side, so this is a representation of the chlorines being on the same side, we know that that's called a cis stereo isomer, right? A cis stereo isomer. And if you think about the symmetry of this molecule, you can certainly see that this cis stereoisomer has a plane of symmetry in it. And therefore, even though there are two stereogenic centers, two stereogenic carbons, we don't really have to worry about assigning them because we know that if there's a plane of symmetry in the molecule, then the molecule becomes a meso compound and it's optically inactive, right? So assigning absolute configurations doesn't mean anything in this particular case. Now, when we look at the trans stereoisomer, we see that So I've put the chlorine on the left on top, the chlorine on the right on the bottom, right? So they are trans to one another. And if I calculate the absolute configuration of each stereogenic carbon, I see that the carbon on the left has an S rotation. So make sure that you can see that it's an S rotation. The chlorine's number 1, the carbon with the chlorine attached to it is number 2, and then that methylene, the CH2, is number 3. So we're rotating in a counterclockwise fashion, and therefore it's S. And likewise, the carbon on the right has an absolute configuration of S. Now notice I can draw, in this particular molecule, there is no plane of symmetry. And so I can draw the mirror image of that. That mirror image is non-superimposable with the image on the left. So this is a different isomer of trans 1,2-dichlorocyclopropane. And so we can assign absolute configurations, right? And as a matter of fact, the absolute configurations change. So they, instead of SS, we get RR. So it's important to note that now what do we have in terms of all of the isomers of dichlorocyclopropane? Well, there are 4 of them, 4 isomers. We have 1,1-dichlorocyclopropane. We have cis 1,2-dichlorocyclopropane, which cyclopropane should say, which is a meso compound, and it is optically inactive, as is the 1,1-dichlorocyclopropane. And now we have 2 isomers of the trans. We have trans 1,2, or excuse me, 1s2s, 1,2-dichlorocyclopropane, and then we have trans 1r 2r, 1,2-dichlorocyclopropane. And so we see that these 2 are enantiomers of one another. They are optically active, right? Because they are chiral. There is no symmetry within the molecule. Now, keep in mind that cyclopropane is planar, and therefore it's kind of easy in this particular case to analyze all of the potential stereoisomers. But when you get into larger rings, they are not planar. And so this complicates matters to a certain extent. And we're going to explore that in the next chapter.